Welcome to part 1 of Bayes' rule. Over the next few minutes we will examine a simple example of Bayes' rule in action. But before we begin, let's consider why Bayes' rule matters. On hearing that sound, most people think of horses. But why horses? Why not zebras? The simple answer is that horses are more common than zebras. When you hear the sound of hooves and think of horses, you are using your own previous experience to interpret a sound that is otherwise completely ambiguous. For example, if you lived in a world where there were zebras but no horses, then you would think of zebras when you hear the sound of hooves. In fact, without realizing it, you are using Bayes' rule. In essence, Bayes' rule matters because it shows how to combine data, like the sound of hooves, with previous experience to arrive at a rational interpretation of the data. Before we work through a particular example of Bayes' rule, here is a quick look at where we are heading. This is Bayes' rule. You are not expected to understand this equation at the moment, but you will understand it by the time we have finished this pair of short presentations. Suppose you wake up one day with spots all over your face. The doctor tells you that 90% of people who have smallpox have spots. In other words, the probability of having spots, given that you have smallpox, is 0.9. As smallpox is often fatal, you are naturally terrified. The doctor, seeing you recoil in horror, quickly adds that spots can also be caused by chickenpox. In fact, 80% of people who have chickenpox also have spots. In other words, the probability of having spots, given that you have chickenpox, is 0.8. So there you have it. 80% of people with chickenpox have spots, and 90% of people with smallpox also have spots. In the absence of any other information, it looks as if it's slightly more likely that you have smallpox than chickenpox. But suppose we do have access to some other information. For reasons that will become apparent, let's call this other information prior information. In this example, the prior information, which is in the doctor's head, is that 1 in 10 people have chickenpox, whereas only 1 in 1,000 people have smallpox. Naturally, this prior information should affect how the doctor makes the diagnosis, but precisely how much the prior information affects the diagnosis is given by Bayes' rule. The fact that the background rate of chickenpox in the population is much larger than the background rate of smallpox is represented here by using a large box for the letter C for chickenpox and a small box for the letter S for smallpox. When we use Bayes' rule to take account of the prevalence of chickenpox and smallpox in the population, we find that the diagnosis has changed from smallpox to chickenpox. Specifically, we now find that the probability that the disease is chickenpox is 0.99 or 99%, whereas the probability that the disease is smallpox is 0.01 or 1%. In other words, taking account of the background rate of each of the diseases in the population changes the tentative conclusion that the disease is smallpox to the almost certain conclusion that the disease is chickenpox. Precisely how Bayes' rule gives rise to these particular probabilities will be explained in part 2 of this presentation. This is just one of the examples from my book called Bayes' Rule, A Tutorial Introduction to Bayesian Analysis. Chapter 1 and computer code which implements the various examples in the book can be downloaded from the book website. 4 versions of the book are available, which contain code in Python, MatLab and R. These books are available on Amazon in hardback, paperback and as an e-book. Thank you.